Okay, so I would like to first start off. I know Jonathan already started to talk about the state design pattern. It's basically the same slides. I'm just using my version from the fall semester, last semester, but basically the same. I just want to review very quickly the problem that we are trying to solve, and also the first two designs and how problematic they might be. And that will give us the motivation to actually do the state design pattern, which is going to be a very nice case study for polymorphism, dynamic binding, and polymorphic array specifically. Okay, we'll get there, okay? And also the source code should be available on the website. You can also check, okay? So let's now talk about the problem again. Let's review very quickly. Okay, I'll spend maybe first 5 to 10 minutes to review the first two solutions, which Jonathan did on Monday, and then we'll get to the final solution using the state design pattern. So this is the kind of problem we are trying to solve. So whenever you have some interaction with the user, you have some under the hood transition function you want to implement, or like a flow chart, right? You want to say if the user is currently in this reservation page, if they say, I want to confirm my booking, you should go to another page to show them, right? So you got different states for your particular system. So online booking system is just one example, but this is a very general problem that we're trying to solve. So state transition diagram is very important. For those of you who took 2001, this is exactly the NFA, non-deterministic finite automata that you learned in the course. And this is a typical example over here. So I'm going to use this as an example to illustrate throughout. So we have this transition diagram over here. You can see that, let's just see one example, which we'll go over today. You can see that over here, you have 6 different states. And for every state, you can have different transitions. For example, let's say if I'm currently in this particular state number 1, in the initial states. Of course, every transition diagram should have an initial states, which you can choose. And then if the user decides to give a particular choice for us to transit, let's say the user give transition 3. So now the transitions can be either 1 or 2 or 3. In case it is 3, we're going to move from state 1 to state number 2. The reason that we say that the system is interactive, meaning that as long as the user does not terminate the program, we can keep going to transit between the diagram, to can traverse for as long as the user wants. So it's completely interactive. Okay, we'll get to some more implementation details in a moment. And then what's the design challenges? In general, you have, as you learned from 2011, the data structure course, if you have a graph, so how many transitions can you have up to? It's n squared, right? N would be the number of vertices you got in the graph. So in general, it's quite a challenging problem to solve. Okay, so I think that these kind of issue were covered already on Monday. So let me skip through it. So now let's go over the very first solution, which is quite typical. Even if you're programming in OO language, sometimes people might program in OO language in a way that's not really OO, which means you're wasting the OO feature of your language, like Java or C# or iPhone. Okay, let's see the first one over here. Let's say we have different labels over here. You can see we got 6 different states, so we got 6 different labels. Okay, so now for each particular label, it contains detail about what should you do for this particular states. Give you one example. Let's say for state number 3 over here, let's say we are in the state for seat inquiry. So the user wants to know about the availability for the states, for the seats. And then for that particular one, you can see we just follow the label over here. And the way we handle for each state is very similar. We can say, we're going to first of all display something particular about this particular state, like a web page. And also we say that we're going to stay in this page until the user tells us the correct input, right? They may have to tell us their credit card number, maybe their login number, whatever, right? Everything has to be valid until we can actually, until then we can actually exit from this particular page. And then we simply read the user's answer and also read what's their choice. For example, their choice might be to say over here, if they are in this state over here, if they give us the choice, let's say number 1, in which case we'll go to state number 6, right? If they give us choice number 3, we'll go to state number 2. If they give us choice 2, in that case, it's not valid. So we get stuck. And then we should really display an error message to say you should choose again, right? That's kind of the pattern for every state in your system. Okay, and then if you got wrong answer, you should read output error message. And then finally, let's say if you exit from this particular loop, that means the answer and the input are valid. So that means we can process the information that we have read for this particular state. Process that, and then you want to actually to say, for this particular state, let's say number 3. Let's say for state number 3, if, let me just move this here. For state number 3, if we read a transition number 2, that means we want to go to the previous states, right? If we read a transition 3, that means we go to the next states, and etc. Yeah?
Why we're picking 2 from the initial state?
Oh, yeah, good question. So for this particular diagram, I have the following convention. Except for when you go from initial to final, you say transition 1. But for every other state, when you say transition 2, that means you want to go to the previous state. If you say 3, that means you go to the next state, just to make it easy. Yeah. So of course, when you are trying to develop your own transition diagram, the name of the transition is completely up to you. Okay. The reason I make these transition numbers, numerical values, also for the convenience for implementation. Of course, you can have some string values for them as well. And guys, don't worry. I don't have any pressure about finishing any number of slides. If you got questions, feel free to answer. Right? I'll leave whatever that's rest to Jonathan for next week. Okay. Okay. Now. So now this will be for these 2 cases, and then, so these are the only 2 valid cases, and then we'll finish. Now, I only show you the details for one particular state, for one particular label. Let's think about what's going to be the code for 1, 2, 4, 5, and 6. It's going to be extremely similar, right? You're going to still have a loop, and you want to process, you want to validate the user's choice and answer, and also you want to say case C in depending on which transition might be applicable for this particular state. So it's very, very similar. Whenever you have to duplicate the code structure in your design, that means your design smells. That's how we say that in an informal way. What we want to do is, eventually, we want to get rid of this kind of duplication and let polymorphism and dynamic binding to somehow do the job for you. So you can see that over here, we got quite a bit of loop and also if then else, basically. You can see when we have the case statements over there, it's basically if then else. If we use a state pattern, we don't need any if then else. Okay, that's something I can preview for you. Eventually we get there. Okay, that's about the first design. You can definitely, so also people say it's about of spaghetti code. Okay, maybe you have heard about the expression before. Because if you think about at the runtime, what's going to be, how is your code going to be executed? It's going to be like this. So now let's imagine that if I use red line over here as the flow of execution, let's say initially we are here, and then somehow we go to state number 4, just for example, right? And then from state number 4, we might go to 6, and from 6, we might go to 4, and then 4, we might go to 2, right? It's exactly like a spaghetti, right? That's why they have the name. Anyway. Okay, that's about the first attempt, which is not too bad, I would say. It might still work. However, when you design your software, you have to think about scalability for your design. This kind of coding might work for a toy example, but for realistic design, it's not going to scale. Okay, that's why we want a better one. So we go to the second solution over there, which I'll briefly review. For the second solution over there, so we have so-called a top-down hierarchical solution. Okay, so basically we're going to say overall how is the system going to interact with the user. Okay, and then we're going to read some input, and then we're going to somehow do some transition of the states. Okay, so the second design is not too bad. It's quite a big improvement from the first one. However, it still has some limitation. We'll see that. Okay. Just cover very briefly. So now, in the second design, the big improvement is now we want to say the transition for the system is just a particular attribute or a particular feature we have. So whenever you want to modify the way you want to transit between states to states, you only have to modify this particular transition function. Okay, that's something I believe Jonathan covered already on Monday. Okay, so now of course you can have some contracts for your transition. You can say what does it really mean? For your state to be valid, that should be between 1 and 6. And what does it mean for the transition to be valid? It should be between 1 and 3, right? Okay, so now, how do you implement this? So the way we implement second and third solution is going to be the same for this respect. How do we implement a transition function? The most straightforward way and efficient way is by using a 2-dimensional array. And remember, in your 2011, you talk about how to implement graph, right? You talk about adjacency matrix, it's called the adjacency matrix, right? Something like that. Okay, that's kind of the the implementation for that. Okay, you can also review your 2011 notes for that. Okay, for example, you can see that over here, the diagram I showed before, I'll show you quickly. It's very easy to see the correspondence. You can see that this is our transition table. It's just a table. Okay? For example, you can see that over here, if we are currently in state number 1, which is called the source states, and then we are trying to make a transition over here. If the transition user request is number 2, and then we'll transit into a target state called number 5, right? That's how it works, the transition table. Okay, nothing's new here. So how do you implement this? The way you do that is by using a two-dimensional array, right? You can see it looks almost identical to what we saw in the previous one, right? So you can use a two-dimensional array. Let's say for this particular class, we're going to follow the following convention. For the row number over here, 1, 2, 3, 4, 5, 6, it's going to be the state number, okay? And for the column number over here, we have 1, 2, and 3. So these are the possible transitions. That's why I made the transition numerical, just to make it easier for you to see. Of course, you can have some additional mapping to go from string transition into numerical values. Okay, so now again, if you try to see the same transition over here, let me just write the notation over here. For example, if you have your transition array over here, okay, you can first go to the source state. Let me just use the same example, 1. You can pass 1 over here, and then I want to know at source state 1, if I try to make the transition 2, what would that be? So I'll pass 2 as a column number. So that means I'm looking up this particular cell in the two-dimensional array, right? That's how I get the return target states, and then I can make a transition. Are we okay so far? Okay. Good. That's about how we implement that, and that's really is immediately applicable for the second design, and for the third design as well. Okay. Okay, so it's a better design because now we separate the control structure into a separate two-dimensional matrix to do it, rather than just having lots of labels and block of code that repeat themselves. Okay, so now this is the conceptual picture for this kind of top-down design, which is not too bad, but you will see that we are causing some inconvenience over there. You will see that as we see the more implementation details, things will also repeat themselves, which again, that means your design smells. So that's why we want to improve further to the third design. Let's see more detail over here. Okay, let's review very quickly over here about what we do for this diagram over here. Okay, this diagram here, basically, how about I move that to the top over here? Okay, so now this diagram over here, at the top level, we have something called execute session. Execute session simply, this defines the flow for the application to interact with the user, which means we'll start with some, and then I'll use a different color over here. At the second level, we're going to initialize some states, okay? Maybe state number 1 or state number 2, any state, initialize to be something. And then we'll try to execute the states. Execute the states simply means based on the current states, we are going to do some state-specific transition or state-specific processing, okay, which is defined in the first level, the bottom level. And then eventually we can make some transition, and also we can say if the state I'm now in is actually the terminating state for the diagram, and then we exit from the application. Right? That's kind of one possible pattern for you to define the application. Now in the third level over here, you can see that for every possible state, including state number 1, 2, 3, 4, 5, 6, for every state, okay, depending on which state you're in, you're going to do the following common operation. You're going to do, for every state, I want to be able to display, I want to be able to read some input, I want to validate if the input is correct, and also I want to display some error message if the input is actually wrong. And eventually, I want to process whatever the correct information that has been entered by the user, right? Again, the pattern itself is really the same between state to state. However, there's some value that would not be the same between states, which I'll show you. Okay, okay, that's about the top. That's why we say it's top-down and hierarchical design. Okay. Okay. Now, let me just go directly to give you some little bit more details. Let's now have some details about the execution session. Okay, this one. Let me just use pen. Let's have a look at this. Okay, let's have a look at this. Okay, now how is this going to be implemented? Okay, not too bad. Okay, it's going to be exactly the same as pretty much like that. Okay, I'm just going to show you some more details. So now, so we're going to have some local variables. We have current states and also got choice. They're both integers. Okay, no objects just yet, just integer. And then we have a loop to say if the current state is the initial states, whatever it is. And then we're going to say until we are reaching the final states, which means we're going to terminate the application. And then we're going to do the following actions for every state. First of all, we're going to somehow execute a state, which we'll define in the next slides. So execute state is basically what will be defined over here. Okay, you'll be elaborated in the next slides. And this one here is going to say, based on the current states, I'm going to do some state-specific processing. Okay, so now you can see that the current state over here is actually passed as a parameter for this particular feature. That's something I want you to pay attention to. For now, it seems to be okay, but we'll realize it's actually quite a bottleneck for your design, okay, in a moment. And then, how do we go to the next stage? So we're going to update the current state to be, we do some transition, which is the transition function I showed you in the previous slide, right? Using the two-dimensional array to look up. Transition from the current state based on the choice the user have. And that's about it. So this pattern over here is going to be how we implement the interaction between the system and the user. Okay? Of course, you can swap the order for your particular application if you like. But again, it defines a pattern over there. Okay. The more interesting code to show you is now in this slide over here. Let's now show you how we define the execute state over here. Okay? Remember, for the execute states, we actually take a parameter for the current states. I'll say CS, current states. Okay? We'll see how that's going to be done. So now, for the current states, execute state over here, we have answer and valid answer, stuff like that. Okay? Let's just see the big picture. Until we actually got valid answer from the user, this is what we're going to do. Display the current states, and then read the answer that is specific for this current states. Also, we want to get also the choice specific to this current states. And also, we want to validate the answer specific to this current states. Also, we want to say if the current state is not getting the right answer, we want to output some error message. Again, you can see current states is actually now passing around, right? And we want to process again. Again, to do the processing, you can see depending on what current state is, we're gonna say gonna pass that as a parameter and then say what the answer is. And then eventually, we're gonna return what the choice is for the user, and then we can make a transition. So now, let me pause a little bit over here. You can see that somehow when we so there will be how many features do we have to define? Display, re-answer, re-choice, correct, message, and process. 6 features. Can you see any repetitions of structure, control structure, that will appear in these 6 features? Any repetition? Exactly. And remember, we got 6 different states, right? So that means for display, you might say if the current state is equal to 1, do something. Else if is equal to 2, do something until 6. Okay? How many times are you going to repeat this particular if structure? 6 times. That means your design smells, right? That's not good. Okay? Let's make it more explicit. Okay? So now let's go back there. Okay, again, this is how we call that. You can see every feature now takes as part of the parameter the current states, which is integer. Okay? And now let's see that over here, display. You're going to say exactly what you suggested. So current state will be 1, and then current state will be 2, and etc. until the last case. So now let's think about another issue here. Remember, we talked about single choice principle. Can anybody tell me what a single choice principle is? Give me a short definition. Yes, whenever you introduce a change to your design, there should be only a single place to change. It can be a class or it can be a routine, right? A single place, cannot be multiple. Okay, let's go a little bit further. Let me try another person. I'm pretty sure you know the answer. Can somebody tell me how this particular second design violates the single choice principle? I.e., imagine what kind of change you will introduce to the class, question number 1. Question number 2, if you have such a change to your system, what would be the changes to make? Yes?
You add another state.
If you add another state, okay, that's a change. And then, yes? How do you change the if statement structure? Exactly. Okay, so now this is how you violate the single choice principle. Let's say I want to add a new state into my transition diagram, state number 7. In that case, for every display, process, and whatever feature I have, I need to add another else if to say else if state, the current state is equal to 7. I need to do this for every particular state. That means I need to modify 6 different features, and that's multiple places. So it violates the single choice principle. Okay? Okay, so I would say since we teach so many design principles in this course, so how do you go beyond this course? Of course, you wouldn't work in IFO anymore. So now, the thing is, think about, based on these design principles, how do I judge if my design is correct? Always ask yourself, does my design smell? Does my design violate the single choice principle, and etc., right? That's kind of the question you can ask yourself to really reflect, okay? That's exactly what I'm doing here. Okay, it violates the single choice principle because if you add or delete states, you're gonna add or delete multiple branches, the same branch basically in multiple places. Okay, so that means, so now if you look at this diagram here, that's really what's happening over here. From the top level, level number 3, when we say execute a session, we're gonna pass the current states, right? And then when we try to say the execute states, we're gonna pass the current states to every feature in level number 1. Okay? And because of that, we have to repeat the if then else structure for 6 times. Okay? Now imagine that if you have a much more complicated application where you have, let's say in the level number 1, let's say you got 50 different features to implement. How many times do you get repeat? 50 times, right? That's not good. Not the way to go. That means your design does not scale to realistic application. That's exactly the thing we want to handle. That's why we need a 3rd version of the solution. Okay. So now, how do we fix this? So there, I believe this more or less where Jonathan left off from Monday, right? Okay. Okay. Let's now try to see what a nice solution would be. And up to now, you learn about inheritance, you learn about polymorphism, you learn about dynamic binding, you learn about the principle program to the interface, not to the implementation, right? So these are all the design principles we have learned. In this particular design pattern, we're going to see all these working together. Okay, let's see. Okay. So now this is something called law of inversion. You can also refer to your OOSC2 chapter for a little bit more details about this. Okay, let me just talk about it very quickly, and then to see how that can be applied to this particular example. First of all, we know that, okay, let's read it together. If your routines exchange too many data, what are the routines we are talking about? Display, process, or the 6 features in the level number 1. Then, if you exchange too many data, what kind of data are we keep exchanging? The states, the current states, right? We're exchanging the state way too much. In that case, put your routines in your data. What that simply means, in the OO context, make the states as a class, rather than just a single integer. Okay? That's something that maybe is a little bit counterintuitive for now, but let's think in this way. This is how I think about it. Thinking this way. So now you can see that for feature a little bit more abstractly, okay, to save my writing. If you got feature number 1 is taking a state, feature number 2 is also taking the current state, and S, and then all the way to feature number N, taking a state. You can see the S over here is repeating, oh, not here. Is actually repeating as inputs in all the features. In this case, how do we don't want to actually pass this around anymore. The way to do it is we're going to refactor our design into the following. We're going to say, now we're going to somehow make all these states over here into a class. Just call it states. And then, since we got so many kinds of states, how can we support these kind of states? We use inheritance. We can say the states at the top level is a deferred class, abstract class. At the bottom level, we got different descending classes over there, right? Whatever you define in the abstract level, in the deferred class, you have to support them, effect them with code, right, in the descending class level. Okay, we'll see more details. I'm just talking about conceptually. That's how you think of it. Again, so later on, if you do your Java development, similar principle. If you see that you're exchanging something way too often in your methods, in that case, you may want to factor out these data over here into a separate single class. Okay, that's kind of the law of inversion we are talking about. Okay, no, and that's exactly what I said. You can see over here we got states all exchanging around. So what we're going to do is we're going to modularize the notation of states as a class. Okay, and I'm going to show you how you can define a class in just a moment. Okay, and we're going to encapsulate everything we want to support about our states. Now, question for you: tell me something. So let's say we move a little bit further from the second design. We are now basically preparing for the third design. Let's say I do define a state class. Can you suggest something for me? So now, according to this diagram for the second design, in the state class, what should we support? What kind of feature should we support? Yes?
The bottom 5, and then state number as well.
State number as well? State number. Okay, you know what? It's a very good responses. Let me say there are two parts, right? The first part, you said for every for the state class, we should support display, read, correct, message, process, right? I agree. Now, you also said to support a state number. I will challenge you by asking, is it really necessary? Thinking this way. Let me just go a little bit like a preview. Let me ask you guys. Okay, let me just go a little bit further to over here. Oh, actually, let me just add a new page. Okay, let me say. Okay, let's say this. Imagine that if I say S, oh, thank you, always happen. S is of type states. Okay, now let's say we use inheritance to support this. So now if I have over here states over here at the top, which is deferred. Okay, and then we got things like display. And also we got process, etc. Right? Okay? Just put 2 for example. And now, should we put the state number? I'll say number over here. Should we put it? Let's leave an open question. Now, let me just make 2 examples. What states can we have? Right? So we got, for example, we have one state called flight inquiry. Okay, and also we have another one called confirmation. I'll just confirmation. Let's put these 2 descendants first. Now, question for you. Do we really need a state number? Remember, the state number before in the second design is for us to say if the current state is 1, then we do something for the display. If the current state is number 2, then we do something for the state, right? So now, you may want to say, maybe just the, what do you want to say? Answer? Oh, I'm pretty sure you know. How about let me, anybody want to say something before I tell you what's going to happen? I'm going to illustrate polymorphism and dynamic binding in just a right away. Can anybody tell me that, given that we got some inheritance hierarchy over here, how is polymorphism and dynamic binding going to eliminate the need for an attribute called state number? How is that going to help us eliminate that? Anybody? Except for, okay, you're a new guy. Yeah. Let's say we redefine, yes. Of course, okay, let me just go step by step so everybody else can follow. Let's say this, the display over here will be also defer, process will also be defer, right? Let's call about display, okay? Now, if I say display over here, it will be plus effective, you know. And also we got display over here, that will also be effective. Now, go further. Can you be a little bit more specific? Okay, now, let's say I have S over here. So now, question for you. If when I declare S of type states, okay, now, let me go a little further. Is state the static type or dynamic type? Guys, review, static type or dynamic type? Static type. Static type is easy to recognize. It's whatever you declare is static type. Whatever you create for runtime will be dynamic type. Okay? So now let's try the following code very quickly, conceptually. Okay? So now let's say, of course, the same principle applies to any OOP, okay, any OO language. So now we say that this state over here is a static type. Static type. And now think about polymorphism. What does polymorphism mean? Polymorphism means you can assign any runtime objects whose type is a descendant class of the static type. For example, let's say, let me use IPO syntax. How about that? Okay, hopefully you are familiar with that. So now, how do I create an object? How do I attach an object of dynamic type initial to S? Okay, let's try that together. Of course, you can say create, and then dynamic type, right? So I would say initial over here, TIAL. That's a dynamic type. And then I can say s.make. So what does that do? What that does is, let's visualize what's going to happen here. When I first declare s, first of all, it's going to point to just void initially, right? It points to nothing. And as soon as, let's say that's 1, that's 2. So this is 1. And as soon as I say 2, let's say 2 over here, okay, use a different color. As soon as I say 2, that means S is now going to point to an object whose dynamic type is initial. Like that, okay? And now, if I try number 3, if I say S.display, and my question for you, imagine that you're a compiler. Would this line compile? If so, why? If not, why not? Line number 3, would it compile? S.display, why not? Why? Exactly, because the display is defined at the level of the static type. Exactly right. Okay. Okay, this compiles because display over here is defined at the static type level. Okay. Okay, now if I say s.display, I know that it's going to display only the initial states, right? Okay. Now let's do some comparison. Now let me reattach the object to something. Okay. Let me now do line number, let's say 4. Okay. Let me use maybe pink. How about that? Number 4. Let's say I want to change the dynamic type. I say creates. Let's say I want to say flight inquiry over here s.make. So what does that do? That means S is not going to point to here anymore. It's now going to point to another object of type flight inquiry over here. Okay. So now if I say line number 5, s.display, it is going to compile for the same reason as line number 3, because now display is still defined in the static type. That's why we say that you should always program to the interface, meaning that deferred class rather than implementation. Imagine that if I simply just do, I'll get to that, just at the end. So now I want you to compare exactly these 2 lines and tell me if the behavior will be different. You can see we got exactly the same line in 3 and 5 over here. Is it going to display different things or the same thing? Intuitively, it should be the same, right? Because they're the same line. Anybody? Different things. Why?
Because even though they're the same object, which is a state, you declare them differently. So that one belongs to initial and the number 5.
Exactly, yeah. Exactly right. So this will be different because dynamic type is different. At the point of line number 3, the dynamic type for S is initial. At the point of line number 5, the dynamic type will be flight inquiry. So the behavior will be different, dynamic binding, right? Okay. Now, let me illustrate another principle for you. We talk about another thing, and I'll illustrate here. It's called program with interface, not with code. Okay. What does that mean? Okay. Now, hypothetically, let's say if I try to say, rather than declaring S to be states, I declare that to be something that's more specific. If I say that should be just confirmation, and tell me which line. Let me not say confirmation. Okay. Let me just say initial. How about that? Let's say initial. So I'm being very specific. Now, tell me which line is going to fail for compilation. Which line? 4, right? Now, why would line number 2 pass? Because initial is the descendant of itself, right? And for line number 4, initial and flight inquiry, they're sibling, right? If you talk about tree, they are not really descendant or ancestor relationship. Okay, so we know that if you do this, it's going to give you much less flexibility. So this is not the way to go. So that's just illustrate again this principle over here. You should program with interface as abstract as possible. In this case, the states, rather than specific states descendants. Okay. Any questions? It's a quick review of polymorphism, dynamic binding, etc. Let me give you a little bit preview over here. For the state pattern, we are basically playing with this kind of OO features, like a polymorphism and dynamic binding. The only complication we're going to have is, rather than having a single S variable over here, we're going to have an array of such variables. It's something called polymorphic array, which I'll get into. But if you can understand this slide here without any problem, it should be okay. Okay, we'll get there. Okay, I think we're doing okay with time. Good. Okay, that's about the architecture for the state pattern, but I think I have said that already, but let's review that very quickly. So now we have client supplier, we also got inheritance, right? We got different parties involved. Let's see who the client is. The client is whoever is using the application, so this is the client, right? Application for, yes. Oh, you can see it? Oh, guys, don't be so shy, just tell me, right? Yeah. It'd be hilarious if I just go for 10 minutes and nobody tell me, right? Okay, okay, good. So application here is the client, okay? Now, what about the supplier? Notice one thing that's really important to see. Notice the client-supplier arrow over here. You can see that I point the client-supplier like this, rather than like this, to a specific state. There's a reason for that, and that's for exactly the same reason as we said, program with the interface, but not with the code. We want to say for as far as the application is concerned, when they define some states information, they want to be very general about what the state should be, states. At the runtime, it can be either of the 6 or 7 descendant classes over here, right? That's something to note, okay? So I want to just put a cross mark over here to tell you that's not the way to go, okay? So now, for the supplier level over there, you can see that we got states over here, okay? That's the static type of the attributes, right? And then for the dynamic type, you can see we got different choices for you. We got initial, and these are just the dynamic types, okay? So everything plays together quite well. So that's the architecture. And then you can see that for the features over here, we have execute, we have read, display, correct, process, and message. And I want to draw your attention to this particular one, execute over here. You can see I say execute plus. That means execute is going to contain some code. However, there is a mini design pattern which we use in this particular state pattern, which I'll show you in just a moment. Okay? But I want you to pay attention to execute itself is of different nature of the pink ones. The pink ones over there, read, display, correct, process, and message, they are deferred, which means there's no code at all at the state level. And we have to effect them in each of the descending classes. But now for the execute, we only define them at the top level, which means all the descending classes, they gotta reuse it. Okay? There's a reason for that. There's something called the template pattern. I'll write it down for now, and I'll illustrate when I show you the code. Okay? So over here, the execute over here is going to somehow call all the deferred feature. And each one of them, each of which to be implemented in descending classes. Descendant classes. Okay? And this has a special name for that. It's called the template pattern. Okay, we'll illustrate that when we see the code. Okay, just conceptually, you should notice that we are also applying some very small pattern over here, very easy to see. Okay, we'll see that. You might have already using your 2030 class or other maybe 2011 class already. Okay. Okay, let me go back to the slides. Let's now go over some code for the state ADT, and we'll see how the pattern So how the template pattern has been applied. Okay. Now let's say we have a deferred class states. So that means at least one of the features is deferred. At least one of the features has no code. That means we cannot treat states as a dynamic type at the runtime. So we got read, we got answer, we got choice and answer. They are just attributes, right? Okay. So and then we got display, we got correct, we got process, we got message, right? They are simply just deferred. Okay. At this level, no implementation whatsoever. Now let's look at the effective feature called execute over here. Let's see the blue one, how it can be defined over here. So now over here you can see that we are showing a pattern over here. So now let's see this. When I say local and then good, okay, we say until we got all the correct information from the user. Until that point, we're gonna keep looping. Okay, and then we're gonna say display the current states. You can see that the display here takes no parameter of current state anymore, because we have already factored out the state as a class, the current class. So there's no need to do that anymore. Read, also we got correct, and also we got message, and also we got similar. Okay, let me just use iPad to illustrate. So that's the code over here. Let's see how exactly it is going to satisfy the template pattern. Okay, so now I want you to look at this. I will try to be explicit over here. You can see that display over here, read over here, correct over here, message over here, and process over here. So these features are completely deferred at this level. Agree? Now let me ask you this. How is the template pattern going to work? Again, let me use a similar example as I showed you before. Let me put some code at the bottom here. Again, let me say I program to the interface. I will say s of type states over here. Okay, and then let's say for line number 1, I'm going to say creates, let's say initial s.make. Line number 2, let me finish all the 4 lines and then we'll discuss. And then I would say s.execute. Okay, line number 3, I would say I will want to reattach s to another object, creates, and then I would say, let's say, what about confirm? And then s.make. And then line number 4 would be identical to line number 2. I would say s.execute. Okay, let's again identify what's the dynamic type and what's the static type. The state over here, green one, is the static type, right? And the dynamic type, as we discussed before, is going to change. At line number, I prefer pink actually. So at line number 1, we're going to change the dynamic type to be initial. For line number 3, we're going to change that to confirm. Okay, so 2 different dynamic types. Now, question for you. When I try to execute the identical lines in different places, s.execute, line number 4, x.execute. Okay. Now, question number 1. For these 2 lines, are they executing the same or different version of execute? Execute, I talk about execute. The same version, right? Which version is that? States, because that one is not deferred, and we don't intend to redefine that anyway in all the descending classes, which means it's a single version of execute we are trying to execute. So that is its template. Okay, let me just write it down. Okay. So now over here, I would say, let me use red. Point number 1. So for 3 and 4, we actually the same version, i.e. template, of execute is called. How about that? Okay, that's point number 1. We are calling the same template, which means we define the template for only once. That's why it's called a template, only once. Now, second question. When we try to execute the same version of template, the same version of execute in line number 2 and line number 4, are the bodies of these 2 lines going to behave the same or not? But they're calling the same features, aren't they? Are they going to behave the same or not? If you think no, why not? Can anybody at the back can tell me? You want to try? Anybody at the back? Yes. Okay, we only got one version of execute at the state level. Now, you're claiming that when I say in line number 2 s.execute, I will be in the context of initial. In that case, which version of the features am I calling the pink one? Which version? Am I calling the version of display, process, read, etc. in the state level, or in the initial level or other levels? In the initial level, right? Okay. And this is called what? Dynamic binding, exactly. What about line number 4? For line number 4, are we calling also the version of initial for display, process, etc.? We don't. Which version do we call? Confirm, because that's the current dynamic type for that, right? So hopefully you see that. So the interesting about the template method is every time when you're trying to do things like number 2 and number 4, you're calling the same template. However, when you're trying to execute the same template, the details for the template themselves are deferred, which means they should be effected at the descending classes level. And those descending classes will correspond to the dynamic types for those for the S over there. So that means at line number 2, the dynamic type will be initial. That means the template is going to behave just like the one for initial. For line number 4, the dynamic type will be confirm. So you behave just like confirm, right? Okay, let me write it down, and then I'll take questions if you have any. Okay, line number 2 over there. So we will say something like, also 3 and 4, different versions of, display, read, etc. will be executed. And this is exactly what dynamic binding is. Yeah, forgive about my writing, but hopefully you see the idea, right? Okay. Guys, any question about the template design pattern? Any questions? It's a nice pattern, actually. You can see how much coding we are saving. If we did not define the execute at this state level, you got to repeat the same execute structure in all the descending classes, which will make your design smell, right? I keep saying this, well, to really let you know it's really bad. Okay? Okay, that's about the state class. Okay, let's go a little bit further. Okay? And okay, this is going to be the runtime structure for the state pattern. I'll get there in just a moment, but I just want to highlight a few things. So this is kind of the final structure for the state pattern. I'll show you exactly how you can build it up from scratch. We'll show you. Okay, but now I just want to highlight a few things for you. Let me go back to iPad over here. Okay, let's see over here. So now overall, let's just read about it. Okay, it's not too difficult. Okay. So now over here you got application, it's objects, and then there are 2 attributes, 2 features for this particular application for any interactive system. The first one is the transition function, and which is 2-dimensional array. And you have seen this array already, right, in the previous slide. That's how you implement a transition function. And nothing so magical about the transition function. The row number will be the states, and the column number will be the choice, right? So now the second attribute or feature is going to be the interesting bit. That's really the meat for state pattern. So this is so-called polymorphic array. Polymorphic array. Okay? Polymorphic array simply means the static type for the array is states. Dynamic type for every element in the array can be different as long as they are descendants of the states. I'll give you one example. Okay? So now let's say this. First of all, let me show you how you can declare the states over here. Let's say over here. So now when you first declare, you will say states. And then, again, program to the interface, but not to the code. So you would say array of states. So the static type over here is as general as we can, okay, at the top level. So now what can we assign to each slot of the array? that's exactly how we can assign to S, which was declared as states, right? So now, assuming that state has been initialized to be certain size, let's assume, okay? So now, when I say states over here at position, let's say we start the indices from 1, okay? Let's say we do that, okay? So let's say states at position 1, okay, is assigned to be something, okay? So now I can say it's going to be assigned to, I can say some new object. I can say creates, let's say initial dot make. Okay, that's valid Apple syntax. You know, pretty much like a new keyword in Java, right? So you can see that in this particular line over here, what are we doing here? We're saying that the static type for states array at position 1 is states. And now we are trying to make it point to some initial objects, right? So the dynamic type is initial. Similarly, we can do the following. I'm just trying to recreate the array. So now that's what we did for initial over here, right? So now, what about for states at position 2? State at position 2 over here is assigned to, let's say we create another object of a different dynamic type. Let's say it's a flight inquiry dot make. Okay? And over here, you can see that this will be valid because the flight inquiry is a descendant of the static type of the array elements. So that's what we have done. Okay? You can see that that's exactly what the polymorphism is again. You can see that over here. Let me just annotate this for you. When we say the states over here, what does that mean? That means every element in the array, has static type states. Okay, that's what it says. That's how we declare that to be. And then for over here, you can see that we are changing the dynamic type for element number 1 to be initial. And we are changing the dynamic type for element number 2 to be flight inquiry. Right? So that's polymorphic. So now you can see that every element in the array is of different type. From the superficial level, you can see we got initial, flight inquiry, seat inquiry, reservation, and confirmation final. However, they share the same superclass called states. Right? You can see this kind of feature actually works quite well when you have inheritance support in OO. Any questions so far? Yes?
So can you make an effective feature in the deferred class state that everything that its descendants inherit?
Yeah. Okay, how about this? You can restate your question just a bit. Okay, how about I go back here? Can you restate your question again?
Is the make feature in state deferred class?
Oh, I see. So question was, what about a make feature? So I'm just just using a generic name for the constructor. So you can think about, you do have, this is completely up to your choice. I can just make the make feature over here to be deferred, and I can effect that in the descending classes. That's one way to do it, right? I'm just trying to create an object. That's what I'm trying to do.
So my question was, when you're in the array and you're calling the make routine, are you using the states make routine, or are you using?
Oh, okay. Creating the array. Okay, let's go back here. Okay, so over here. Okay. Over here, right? You're talking about these two assignments?
Like
yeah.
Those two make.
Oh, this make. These are the states, of course. Yeah. So this make. This will be the make from initial, and this will be make from flight inquiry, because the way you create different states might be different. They have nothing to do with the array. Array is what's gonna happen in between, which I ignored. Right? Of course, that's how you construct the array to say array that create that make maybe certain size, right? It's different. Yeah.
So it's using the make from each descendant class.
Correct. That's correct. Yeah. So the make feature over here, don't get confused. We are simply calling the state-specific constructors for creating the objects. Right? Guys, any question about polymorphic array? So if people ask you to summarize about a state pattern, basically polymorphic array is one of the things you got to talk about. Right? You have a polymorphic array about states. Now let me go a little bit further. Okay. Now, remember in the second design, we talk about the current states being an integer. So now, what should the current state be in the third design? Let's say the state. How about that? Okay. Let's say it's a state. Well, since I've got to change something, right? I'm just going to sketch the idea for now, and then we'll see some coding in just a moment. Let's say if I have some pointer, let's say I define the current state. Let's say this. If I say current states, now in the third design, I would say it's of type states, which means it can be pointing to any of the states, right, in the array. Let's say the current state is now currently pointing to reservation, for example, right? Okay, that's one possibility over here. So that's the current states. Okay, now if I say current states, dot display. Now what's going to happen? Which version is it going to call? Reservation, because that's a dynamic type. And it compiles because display is defined as the static type of current state, which is state. Okay? Now let's see one more detail. How do we make transitions? Okay? Whenever you make a transition over there, let's take this one for example. Okay? Let's say we want to do a transition from state number 1 to state number 2 using transition 3, for example. Okay? Let's say that's what we want to do. How do we do that? So that means I want to go from 1 into 2. That means I want to reassign the current states from initial into flight inquiry. How do I do that? Okay, basically, it's how it's going to work. We know that for every state over here, they have the corresponding index over here. 1, 2, 3, 4, 5, 6, and there's no coincidence over here. You can see that the size of this particular array over here corresponds to the heights of the two-dimensional matrix over there, right? Because the two-dimensional matrix over there shows you how many, the number of rows shows you how many states there are. So now, if I want to make a transition, this is how I do it. I'll just show you quickly. If I want to make a transition, I say I want to make a transition. Okay, I'm going to give, let's say the source state is actually 1, and the transition I'm trying to take is 3. Okay, so that means the target state should be 2. That means I should really change the current states to index 2 of the array. In that case, this will be the new current states. That means current state should point to here. Okay, that's kind of how the runtime is going to do. So we have separated two concerns. How you make the transition is totally done by the two-dimensional matrix. And then after you get the corresponding value back from the array, after the lookup, for example, if I do if I do this particular transition over here, I get back 5. That means the current state should be changed to the state stored at index 5 of the array. Okay? Okay, hopefully that's clear. Anyway. Okay, let's see some little bit code. How about that? Okay, let's see some code over here. Application class. So now we got application class over here. So that's about how we define this particular application over here, right? As we can see, we got transition, we got states. Right? Let's see how we do that. Okay, we have transition, which is a two-dimensional array of integer, right? Just matrix. And then we got a states polymorphic array, and the static type is states. And then we do initial. The initial state basically is the index into the array of the states and tell you which one will be representing initial states. And then the number of states and also number of choices. And also we have the make, constructor. I'll leave you the details. It's rather easy to follow. Now, invariant is going to be interesting. Can you think about any invariants over here? Invariant means we want to somehow constrain how the features are related to each other. I'll give you a little bit hints. Can you put any constraint between transition and states? Is there any correspondence between them? Yes, go ahead. Exactly what I said. Good man. So now, how do we do that? Now, for example, you can say height and width are simply the feature in two-dimensional array in iPhone. So you can say the height, the number of rows should be the number of states, and also the width of the two-dimensional array should be the number of choices. Okay, that's a straightforward invariance. So you can really constrain. You cannot just put any arbitrary array or any arbitrary two-dimensional array. That's about the application class. Oh, let's continue a little bit further. And then how do we initialize the array, which I'll illustrate to you. So you simply can have some put state, which is pretty much like the put feature for array. Okay, you can see the implementation use force. And then we can choose the initial states to be any states, just by passing an index. Okay, I'll also show you that. Okay, and also we can add up the transition to the array, and also, okay, that's about it. I wouldn't go over detail, but I'll show you from scratch how you can develop something from scratch by drawing some diagram. The coding, you can just read it yourself. It's not really worth discussing. Okay. And then we have also something about execute session, right? For execute session, it's going to be like this. We have current states, okay, which is, you can see the static type is states. And also we got index over here. So now we say from index is initial, so which means we'll go from the initial states, okay? And then we say until we reach the final states, which means we should terminate the application. And then we say that the current state is assigned to states as index. Now, this is exactly where polymorphism happens, and I illustrated already. You can see the index over here can be any of the indices in the array, can be ranging from 1 until 6, right? In the case where the index is actually, for example, 1, in that case, the dynamic type will be initial. In the case where the index is 4, in that case, the dynamic type will be reservation, etc. Okay? And also, dynamic binding is when you try to execute the states, what you will do is, and that's template pattern, remember? Right? So you would say current state execute. Now, we'll be executing the same pattern that's defined in the state class, but now the features for each one of them will be, yeah.
If I wanted to test individual classes, like only the reservation one, how would I make a state for it to actually test something?
So your question is if you only want to test for the one of the specific classes.
Yeah.
So you can still declare S to be your type states, and then you will simply attach S to some confirmation object, for example, right? So you're just gonna, so the dynamic type is really what matters. It's gonna determine the behavior at runtime. Okay, yeah. Okay, guys, any question about these two yellow highlights over here about how the polymorphism and dynamic binding? So that's really, yeah.
So your polymorphic array,
Sure, iPad. Let me do that. Yeah.
so the initial finding query, seeding query, all
Mhm.
those 6 states, the array that you have, does it state all the possible states? Or are you making each individual object that corresponds to those states?
Good question. The question is, how did I figure out these are the 6 objects you put? The answer is, look at your architecture diagram. If you look at that, how many states do we have? 1, 2, 3, 4, 5, 6, 7. Oh, actually, I missed out the help, but anyway. So basically, based on my design over here, I know that from my transition diagram, I can only be in either of the 7 states over here. That means at the runtime, I should never go beyond these states. That means my array of states should be of size exactly this. So how do we determine the size? Look at your design. Okay, that was a good question. That was good. Okay, let's go back over here, and then let's go on. Okay, let's go through a little bit more syntax, and then finally I want to go over a test case with you thoroughly, and then we're done. I'm not sure how long it will take, but let's see. Okay. So now, how do we create an instance of state? We have seen this already. You declare green here is the static type, the red here is the dynamic type. And also, how do we initialize an application? So when you try to create a new application, you have to say how many states do we have, and how many choices transition do we have, right? So these are the ordinary parameters. And also, how do you do polymorphic assignments? So we are simply calling the put states, and the put states for application is going to assign the state to the initial value, right? The current state, right? That will be polymorphic assignments. And then you can choose initials. I will see that. Okay, and then also you can build a transition table, and that's how you do the two-dimensional matrix over here. Let me just go back here. Okay, that's how you build this particular matrix over here. Okay, and then also you can run the application. Okay, let's see. I want to go over that with you. So now let's run this out. You can also download the source code and run it and see the debugger to see how the runtime structure will look like. But let me visualize that for you. So now let's say we have application, we got current state, and we got index. Okay, let's say we got these variables to play with. Okay. Now let's say the first line, we have create application.make. Okay. Let's do line by line. And then I want to have a new page. Okay. For this one over here, I know that I'm going to create a new application object. New application objects, and then it's going to point to some application object over here, right? Application, and we got two important attributes over there. So we have, first of all, we have the transition, and also we have the states. Okay, let's see how this is going to be initialized. First of all, we have 6 states. We have 3 transitions. So that means the corresponding state array should be of size 6. So states is going to point to some array object over here of size 6. 1, 2, 3, 4, 5, 6. Right? Initially, everything point to void, initially. And then also, we have a 6 by 3 matrix, right, to create initially. Okay, okay, 6 by 3. Okay, I'll try to be careful to draw that. 1, 2, 3, 4, 5, 6 by 3. That's a matrix, right? You can see the indices for the row, 1, 2, 3, 4, 5, 6. These are the states. And also we got, let me put it here, 1, 2, and 3. So these are the indices for transitions. Initially, they will just be 0, initially, right? Nothing has been put just yet, nothing, okay? So this is gonna be the effects for just this single line to create an application. Now, how do we put in the states and how do we put in the transition? Let's see very quickly. Now, first of all, let's put in the states. So now, back to your question there, since we know from the architecture we got 7 or 6 different states, we're going to create six different objects. The first one, I'm going to put this particular object of dynamic type initial, and then try to put it in position 1 for the states. That means over here, I'm going to draw position 1 is going to point to a state object. And the dynamic type is initial. And then, of course, you got different information over there. I'm just going to ignore that for now. Okay? And then you will do the similar thing for all the other 5. Yes?
Before you put it with state,
yeah.
Is the array just full of void pointers?
Okay, you know what? I'm more thinking about from the Java point of view. Java will be just null references. But in IFL, remember we talk about void safety. So initially, it would be some default values. I can think of it as like, excuse me, it's going to be like a void. Yeah. Okay, that's good. Okay, and now let's see the next one. Imagine that we're going to create the other 5, right? Okay. After the other 5, we're going to have basically these boxes over here. Every one of them is going to be of different dynamic type. Like that, okay, after that. And now, let's go back there. How do we put in a transition? Oh, also choose initial. Choose initial simply means we're going to say the state at index 1 of the array is going to be the current state's initial value. Okay, so that means now we're going to say current states, which is a variable we declare current states, is now going to point to initial. It's another pointer, right? It's going to point to initial. That's how we choose the initial. And then we're going to put transition. We're going to fill in the table. This particular convention I'm following for this particular code. The 6 over here, let me just write it down and then I'll show you. Okay, let me write it down first and then I'll switch to iPad. So when I say dot put transition and then 611. Okay, so now if you look at the iPad over here, so the convention for this particular example here, 6 is the target states, and 1 is the source states, and 1 over here is the transition to make. Okay, just convention. For your particular app, you can do whatever order you like. Okay, so now what does that mean? That means if I'm currently in the source states over here, 1 over here, That means I'm talking about this particular index over here, right? And then I'm trying to make a transition using choice 1. That means I'm talking about this particular column over here. In that case, I'm going to put 6. That means that's the target states, which means I'll fill in 6 over here. Okay? Okay, you will fill it for the rest. How do you fill in the states? How do you fill in the transition? Depending on your transition table, right? Okay. Okay, that's about it. And then, of course, you can do the rest. Now, let's say, yes, go ahead.
I was going to ask, do you have to do pretend info all the time?
Oh, yeah. And of course, you know, the example we are doing now is a toy example. In the real case, of course, you may have a very big transition. Well, no way around it. Yeah, no way around it. But you do it only once, hopefully, because your application is supposed to be stable, right? You shouldn't really change your transition all the time, right? Okay, good. And then we'll, okay, over here. Okay, so we're gonna say initial state. Okay, we already set the initial state, the current state to be initial, and then, okay, that's what we did. Okay, I kind of was one step ahead. So once we know the initial should be at index 1, so we set the current state to be that particular state. Okay, that's what we did over here. Okay, now let's go a little bit further. So now we can also do some check to say the dynamic type. It's like an instance of check, right? In Java, you can say the instance of current state should be initial. That should be true. Okay, and then let's say we want to do some transition. How do we do that? And the way we can do transition is like this. Okay, do I have any example over here? Okay, so let's say I want to do the following transition over here. Let's say I want to go from, let's say, state number 1 to state number 2, and then using the transition 3. Okay, how do I do that? Okay, the idea is very easy. Okay, so now I know, so which cell should I look up, right? So now to do this one over here, of course, I need to call the transition function over here. You can see the transition function here, right? So now over here, I will highlight. So there's a transition function I need to call. And to return, what should be corresponding lookup? Yes, thank you. Yes, that's a transition function I should call. So now the thing is, I'm currently here, and then I want to make a transition 3. So now, how do I look it up? You can see that if I'm currently in 1 and I'm taking choice 3, that means I should look up what the value is for this one here, right? Okay, it will turn up, okay, you can look at the definition. Your turn up is simply just 2. That means we should really switch the states from wherever the current state is to another place in the array, right? So let's say this is really 2. In that case, we should really change the current state. For example, rather than pointing to here, it's going to point to another object, right? So we got polymorphic array, and also the current state is doing polymorphic assignments over here. That's how we do the state transition, okay? You can see the transition itself is calculated using the 2-dimensional array at the integer level. However, as soon as we figure out what the new current state should be, we do the polymorphic assignments, right? Yes?
In our current program, there's nothing stopping us from making 2 initial states or more multiple initial states.
No. Remember, okay, good question. The question was, in the current coding or design, is it possible to have 2 different initial states? The answer is no. Okay, I'll show you why. It's a very basic question. Okay, but you know, let's get it well handled. If you look at the definition for application over here, you can see where we got that initial variable. The type is integer. Can you store two integers in an integer? No, you cannot, right? Well, anyway, if you really want to have 2, well, I think back in your 2001, you cannot have more than 1 initial state, but you can have more than 1 terminating states. Right? Remember? Yeah, good. Yeah. Of course, for your application, you can do whatever you like. Right? I'm just saying that's a standard. Okay, let me just go back to that last slide over here. Guys, any question about the coding? Are we okay? Okay, let me summarize and then we are done. Okay. So now this is really to compare the second solution and the third solution. The second one is not OO. We do top-down hierarchical design. That might be what you can best achieve using a language like a C, right? Which does not support OO. But now we try to really add in the power of polymorphism and dynamic binding. So this is one thing I want you to think about to really get most insight from state pattern. In the second design, we got lots of if then else statements. In the third design, the if then else statements somehow are still there, but that they are not explicit anymore. They're somehow implicit, but who was doing it? The polymorphism and dynamic binding at the runtime, they are handling the if then else. It's pretty much like current states instance of initial, and then I do something. Current states instance of confirmation, I do something. It's pretty much like current state equals 1, current state equals 2, right? It's really the same thing. You're not really reducing any code to be checked, but somehow you're just reducing your burden as a designer, right? Because you can make use of the polymorphism and dynamic binding. Now let's go over this, and then we're done. In the second design, you have to explicitly put your discrimination using if then else, right? And then if you're gonna say display 1 or display 2, right? So somehow display will have to have different if then else statement to discriminate, to decide. On the other hand, in the third OO solution called a state pattern, what we do is we simply declare S to be of static type states, which in the architecture is the top class over there, which got a number of descending classes. And now, when you call s.display, notice that we say s.display without any more parameters. You can see the S with the context object over here tells you exactly what you should do because of dynamic binding, right? Okay, guys, any questions before I put you back to Jonathan on next Monday? Questions? Okay, that's good. So I'm going to make the lecture recording available in the iPad notes, and then you can just go to my lectures page, and then you'll find it. Okay.